Flying, Driving, Walking AM. And we're looking forward to hearing from her about driving AM solutions to scalable automotive production. So I will invite her to the stage now.
Hi, Melanie. Can you hear me?
We can.
Great.
Thank you so much for joining us, Ellen, and I'll let you take it away from here.
All right, I'll share my screen. All right, I assume you can see this?
It looks great. Thank you.
Okay, great. Well, good afternoon and good evening, everyone. It's a pleasure to be speaking to you today at the first annual TYPE conference. So thank you, Melanie, and thank you to Nora for inviting me to participate in such an exciting lineup of speakers and topics in additive manufacturing. So, while the pandemic has certainly changed the way we collaborate and network, having these virtual platforms has really helped enable us to continue innovating together despite the travel restrictions, and so that we can continue accelerating the adoption of additive manufacturing technologies across all of our industries. So that's been great in the past year. So my role at Ford is in our research organization. So I'm focused not only on how additive manufacturing can create new sources of value across the enterprise, but also in developing emerging technologies to try to address the gaps that keep us from achieving scaled volume production. So today, hopefully I will provide some insight on Ford's journey to drive additive manufacturing solutions to scalable automotive production. So every journey starts with a roadmap. Today, I'm going to talk about why AM, why we care about additive manufacturing at Ford Motor Company. Then I'll talk about our history using additive manufacturing for over 30 years, leading up to where we are today. So I'll provide some examples today where additive manufacturing is creating value in different ways, including some details from a case study and what was required to validate a new process and new material for a series production application. And then finally, the big challenges that remain, especially specific to the automotive industry needs that we need to address in order to get to that volume scale. So the first question is, why is Ford interested in additive design and additive manufacturing? Our mission is customer-centric. What does our customer value most in personal transportation solutions? Performance, styling, quality, customization, cost, or value, among others. Well, the design freedoms and the freeform capabilities of additive manufacturing can enable us to find solutions to achieve these customer-driven attributes. And we think that these can deliver us the business efficiencies and engineering efficiencies to make the case. So we've already been experiencing for quite some time how additive manufacturing can provide those engineering efficiencies in our design and validation stages, from visual aids to fit and finish to more and more functional prototyping for validation to allow us to go through quick iterations and testing. So this helps us to reduce our lead time in responding to changes that the customer may want. On the manufacturing floor, we get efficiencies through things like printed tools and fixtures that not only reduce costs and let us be able to manufacture these fixtures even quicker, but allow us to improve the quality for the manufacturing processes. The toolless production can enable distributed sourcing and very low volumes for customization and quick service. And then finally, improved and integrated functionality through design complexity can give our customers unmatched performance. So in answer to the question if AM can change the automotive manufacturing landscape, yes, it can. It already has for quite some time. but probably in a way that's different than was originally envisioned, not by replacing conventional manufacturing processes, but by enhancing and integrating into our existing processes. So just some history of additive manufacturing at Ford in a timeline. Ford had found early on that additive manufacturing could completely change the way that we do our new product design process through those rapid prototypes, starting in the late 80s with the earliest additive manufacturing technology, stereolithography. Soon after, because of the game-changing way that this helped us in our design, we developed and opened an additive manufacturing training and development center, and then quickly developed several local centers to support all of the needs for rapid prototypes across the globe. Then in 2004, a significant shift in engine prototyping resulted from the introduction of sand printing or rapid sand casting. And so that further reduced our design time for new engine designs. And then more recently, in 2014, I launched a dedicated program in our research organization that allowed us to start to advance additive manufacturing technologies beyond just prototyping. And then we started there, from there on, to have more engagement with early access opportunities to emerging technology providers. And we focused especially on additive manufacturing for production applications. More recently, in 2017, we added laser powder bed fusion metal printing to our in-house capabilities. And in 2018, we introduced our first production applications, which I'll talk a little bit more about in a second. So today, in addition to having 5 prototype shops around the globe that support our vehicle design and engineering validation, we have an enterprise approach to advancing additive manufacturing to gain those efficiencies and create value. The first is from our manufacturing organization. Our Advanced Manufacturing Center, shown here, houses the latest additive manufacturing technologies and sits side by side, so focuses on integrating with our other advanced manufacturing technologies, including things like automation, collaborative robots, virtual and augmented reality, and others. And so while the focus here in this facility and this organization is on manufacturing, we are able to co-locate colleagues from other organizations to work hand in hand to start delivering these new manufacturing solutions. In research, we have facilities in both Dearborn and in Aachen, Germany, that focus on more fundamental development of additive manufacturing technologies, including materials, processes, simulation, and design. And then in our product development organization, our additive manufacturing teams focus on how to design for additive manufacturing processes those products and then implement them into our use cases. So a couple of additive solutions that we've seen across the company. We've shown significant value using additive solutions for manufacturing fixtures, like the one shown here, as well as for hand tools, lift assists, and end effectors on the factory floor. And in fact, we have over 45 printers at more than 30 of our manufacturing plants that support these types of activities. So additive is a solution that can simultaneously address how to make these complex and heavy manufacturing aids to reduce their weight, to reduce the cost and the lead time. But the number of parts that we need to produce, the number of fixtures and manufacturing aids and tools is extremely low volume, 1 or 2, but their physical size can be quite large. So these point to a solution of material extrusion with functional materials, including carbon fiber composites. As we move up in volume from 1 or 2, we now can justify the business case to address more niche market opportunities that were not possible with conventional manufacturing that used a tooled solution. So in this example, what I'm showing is for our F-150 Raptor in China, there was a need for a different component due to some of the regulations that were different from our North American base model. But because of the low volumes in the China market, in the low thousands, cutting a special tool didn't meet our economic targets. And so we turned to additive manufacturing as a solution, here using Carbon's digital light synthesis and EPX82 to quickly design and produce the part that you see here. And if you can see my video as well, I do have a part that, so you can imagine kind of the size and some of the details of that part. So in this auxiliary plug, as I mentioned, as you can imagine, we were able to quickly iterate through several designs to make sure that we hit the functional performance that we needed for the application. But not only that, we were able to meet our low volume cost targets, but we're also able to include this customized aesthetic with a logo and the texture printed directly onto the part. So if you can see this, the challenge was really to ensure good repeatable feature detail for this appearance application, as well as ensuring that it has durability to UV exposure, heat, and humidity in the vehicle environment, interior environment. So this was the first time an additive part was used for production of an appearance part without having a secondary treatment or coating on top of it. In addition, for example, then we were easily able to go to other model variants, like you see here, with the same texture or with different textures very, very easily from one to another. So taking this to a step further, then in that example, you can think about how additive manufacturing can enable customization and personalization. And we've heard many examples of the use of additive to form bespoke items or customized applications, from medical implants to sporting goods to consumer items, and even to automotive parts with what BMW and Twicket have done. Because some customers are really willing to pay a bit more for something personalized to make it better fit with their lifestyle or their persona, or just their own personal fashion. So things like having a better fit shift knob to your hand, like you see in the picture in the upper left-hand corner, or just stylistic changes. So in the example that you see in the upper right-hand corner, you see a quite unique case. Due to increasing thefts, some wheels on our vehicles now have locking wheel nuts in order to deter thieves. This is a case in which there's a need to have a unique key for each vehicle, so something quite bespoke to every single vehicle. So in this case, laser powder bed fusion in metal was used to personalize this key, and it was able to be further personalized by incorporating the pattern of the sound wave of a customer's voice. As we move up in volume, we can also see where additive manufacturing can provide a solution for production of service and spare parts. In this example, we see a lever arm for an HVAC case that was from a late model vehicle in which the tooling had been lost and the service part inventory was almost depleted. Like heavy manufacturing, aerospace, defense, military, there are some extremely long service lives of our products. So we're required to continue to provide spare parts for 10 years or more after discontinuing the model. So in some cases, when planning inventory for spare parts, we guess wrong. And so additive manufacturing can provide us with a quick resolution to be able to replace production parts with a printed spare part. So again, like the picture that you see in the slide, here's a physical example of that part. It is rather small, but again, you can see some of the very detailed features that were able to be printed onto the part. So in this case, we're able to supply depleted inventory, but you can imagine for additional future use cases of spare parts, we can completely eliminate inventory and warehouse requirements and significantly reduce lead times for transportation of spare parts to the point of service, as well as reducing minimum order quantities to whatever is needed for that time. Especially as we move towards distributed manufacturing, this will be a significant improvement. So what the ultimate question, though, is whether additive manufacturing can achieve series production. So far, we've shown this is possible for low volume series production, but we continue to develop strategies to get to that medium and high level of volume. So what I'd like to do now is focus a little bit more on a specific case study where we had that low volume series production application. In this example, this is a part that we're producing today for the Shelby Mustang GT500. It's a performance vehicle, so it's still a relatively low volume, but a series production application. The volumes are in the low thousands, or I'm sorry, the high thousands to low tens of thousands of parts. It's because it's for a performance vehicle, this vehicle has a unique braking system, among other upgrades from the base model. So a new design for this particular part was needed. So additive manufacturing provided us with a solution for this new design, but also gave us some improved performance. So as you see here, we're able to convert from a metal part to a plastic part with over 60% reduction in weight. Here is the part, again, a relatively small part. There are 2 per vehicle, and we had a significant cost savings compared to tooling this part. In addition, we had a reduced complexity. Our original design for the base model had a left-handed and a right-handed part. And in going to additive manufacturing, in addition to a moderate BOM consolidation of 3 parts to 1 part, we're also able to convert it to a single design that can be used either on the left-hand side or the right-hand side, driver or passenger side of the vehicle. So the big challenges here that we had to overcome for using additive manufacturing included the validation of the material, the functional requirements, and the manufacturing requirements. The first step was material validation. So several candidate materials and technologies were screened and benchmarked against conventional manufacturing before ultimately selecting Carbon's EPX82, epoxy-based resin, using digital light synthesis. Because this bracket is an exterior application, underbody, but the other applications that we saw previously also use the same material. We shared the material validation. So we ended up doing a full suite of interior and exterior testing, including weathering, fogging, odor, flammability, as well as exterior underbody, fluid and chemical resistance, and heat and humidity aging. So you see here, a huge number of tests to understand whether from a material point of view, we could survive durability in harsh environments for automotive applications. So once we passed the material and performance testing on this material, we moved to functional validation. For this electric parking brake bracket that I showed, the testing consisted of component level testing that you see in the picture here on the upper right-hand corner. That was a benchtop vibration test and cyclic test. In addition, vehicle level testing on the track was performed. And then finally, assembly level testing, including ergonomics and torque testing. So it's important to note that all of these tests had to meet or exceed our performance for conventional parts. And interestingly, we saw significant advantages in the functional testing stage using additive manufacturing. If you think about it, the first parts that you test are not necessarily prototype parts. They are the first production parts because they're using the production intent or the production process and materials. But we're still able to go through design iterations during that process. So in one example, one of the designs failed during vehicle level track testing. We're able to remove the part, quickly analyze the failure mode, redesign the part to address the failure mode, print the part and reassemble it back onto the track car by the next day and continue the testing, something that could not be done in a conventionally manufactured part. And point in fact that, that several design iterations were tested throughout the validation stages of this application. So for example, here's one of the early designs of a handed part. You can see that it has, typical injection molding type of design with locking nuts and how it interfaces with the other components. We went soon after that to a more topology optimized part and was able to go to this mono design before getting to the final design that you see here. And then finally was the manufacturing validation step to ensure that not only were we able to have a design that met the functional requirements, but we also had a design that was manufacturable and that we're also able to maintain our quality standards in that manufacturing process. In doing so, we went through our typical processes, including creating DFEMAs and PFEMAs, and followed our standard PPAP process in the automotive industry. Again, additive manufacturing resulted in a couple of benefits that we didn't think about from the beginning. So for example, instead of a physical tool that we typically have in stamping or injection molding, here the CAD or the STL becomes our digital tool. However, we are now able to individually serialize and label the parts to indicate the printer, the project, the batch, and even the position on the platform for that particular part. So now as parts are assembled onto the vehicles, we have a way to track their provenance as they go through the assembly process and then through the use case to our customers and finally to the end of life. Furthermore, the digital thread lets us put even more security into the entire digital chain to ensure that the right materials, the right files, process parameters, and so forth are used, and then that the parts are assembled correctly onto the right vehicles. Still in development, however, is, and we're actively doing so today, but I can't share anything today with you, is linking the physical and the digital twins together to be able to confirm genuine parts and prevent counterfeiting. So we've seen some early examples of additive manufacturing providing value, but to date, these have been limited to low volumes. So just a note, when in the automotive industry, we talk about low volume, anything that's lower than than 100,000, for example, we would consider low volume. So low volume has a huge range. We have vehicles for motorsports, for example, that have a volume of 1, all the way up to just under 100,000 that we consider low volume. So for example, what I'm showing here is a comparison of the specific automotive industry needs compared to the aerospace industry. But this could just as easily be a comparison to the medical industry, defense, sporting goods, consumer products. We all have similarities and differences. So the biggest one that I wanted to point out was scale. So as I just mentioned, low volume to us means anything lower than 100,000 or so. So typically for us, to make a big impact, we think a lot about how do we scale additive manufacturing to medium or high volume applications in the hundreds of thousands, even up to 1 million. Compared to the aerospace industry, the scale is much lower, but we have other similarities. The range of size of parts, the different types of requirements for each of those parts is quite similar. But another big challenge for us is our cost sensitivity. This is something that we're really quite sensitive to because of the scale and because of the value to our customers. Further, we have specific needs to be flexible in our manufacturing processes, not only to integrate with our conventional manufacturing processes and infrastructure, but also to have built-in quality in these conventional and new manufacturing processes because of the way our supply chain works. And then finally, a challenge to the additive manufacturing value chain is that we have specific material needs that are not currently met by the materials that are available today. So this combination at the moment is keeping us at these low volume applications. So this is kind of a call to arms for the additive manufacturing community to address some of these big challenges that we have to help us to scale. But the scale challenge is not completely new to us. So a little bit of a history lesson. While Henry Ford didn't invent the assembly line, he did use and improve upon the concept to enable scale production in his day. So by breaking down the process into discrete steps for each operator, he was eventually able to drop the price of a Model T by more than half and reduce the time to build one from more than 12 hours to 90 minutes. Today, if we do a comparison, for an F-150, one of these rolls off the line every 52 seconds. So it's just to give you an idea of the scale that we're up against. However, 52 seconds is not the target for the speed, but rather the takt time. But it's not just faster and more efficient processes that will get us there. I talked a little bit about the other challenges that we have as well. But it requires the development of these automotive grade materials that meet our functional requirements. It requires the development of automotive standards that allow us to certify and validate quality and performance in a systematic way, to have that built-in quality as opposed to 100% inspection. It requires us to develop make use of software tools that allow us to design, simulate, build, monitor, and distribute inside our manufacturing environment. And it requires more end-to-end automation to remove the variability and to eventually allow us to move to lights-out manufacturing that will be important for scalability. All of these together are necessary components to deliver the quality and the throughput that we need to meet automotive scale. But with these, we can adopt more of the new sources of value that I touched on previously for things like service parts and low volume production, for mass customization and distributed manufacturing, and finally for scaling to really gain the value of improved and integrated function. So just wanted to end with the other most important thing is for us to really embrace the paradigm shift, to think additively. This is such a big challenge that Melissa ended hers with a quote. And this is one that I come back to over and over again with things that are so tough like additive manufacturing, is that we need to take the steps forward and take the small successes when we can, because we understand that the ultimate goal is a big challenge. So to paraphrase Socrates, don't let perfect be the enemy of the good. Let us take the good at each step. So I will stop there and thank you for your attention and acknowledge the rest of the Ford team here.
Ellen, thank you so much for that awesome presentation. I think my favorite part about it was that you actually had some of the parts in your hand that you could show up and hold. So that was awesome. Thank you for that. It makes it very real versus just seeing it on the screen. So thank you. There are quite a few. Yeah.
Sometimes it's really hard to get an idea of, I think part of it is emphasizing how small these parts are. So we're able to scale to okay volumes, but they are, something that you can hold in the palm of your hand.
Right. No, that was awesome. So thank you. There are quite a few questions in the Q&A. We probably only have time for one, so I'll ask you the question that got the most votes. And that is, can you talk about what the most used AM technology is at Ford and what technologies you have in-house?
Let me start with the easier question. So in-house, we have I think we have all of the polymer additive technologies, including powder bed fusion, so SLS, as well as multi-jet fusion from HP. We have FDM or material extrusion of all types. Maybe not every single one, but many of the manufacturers. We have polymer jetting, so objet, that type of technology. We have vat photopolymerization, including both stereolithography as well as digital light synthesis and other DLP and benchtop SLA systems. And we have binder jetting. And then on the metal side, so the binder jetting is used primarily for sand printing, as I mentioned at the beginning of my talk, but we're also investigating binder jetting for metal technologies. And then we have laser powder bed fusion for metal additive as well. I think the most used additive technology I want to say is material extrusion. That's the most accessible. We have a lot of maker spaces. As I mentioned, we have a lot of printers at our manufacturing facilities to enable the printing of fixtures and manufacturing aids and so forth. And those are all material extrusion based. It is the most accessible for, one or two parts that may need to have very high, load bearing, requirements, but is not necessarily one that we see today for high volume scale, right? So it's maybe a little bit misleading to talk about what's the most used technology.
Right. Okay. Well, you're using quite a range of technology, so that's pretty amazing that you do all that in-house. So thank you so much again, Ellen, for joining us.